Okay, so this is Unit 2 where we focus a little bit more on liquids and solids. Here we have a few objectives that are going to be a continuation of Unit 1 and carry through those same things that we talked about in 111 and start to apply them to the properties of liquids and solids, and then carrying into colligative properties in Unit 3. So here we're going to describe intermolecular forces and look at the specific intermolecular forces that are going to be present in each molecule we see. We're going to look at how those forces affect the properties of some molecules. Here we're going to be focusing on how it affects melting point, boiling point, and then in a couple of classes we'll start talking about how it also goes into colligative properties and what else it can imply. We're going to look at cohesive versus adhesive forces in liquids, and then we're going to go into solids very briefly. The objective that the VCCS gives us is to classify solids based on characteristics. We're going to use broad topics here. Your reading talks about the specifics. I'll get a little bit more detailed than you need to know, but your homework should indicate the level of detail that you really need to focus on. It's always better to focus on more detail than not enough, but there are so many types of solids that this right here could be very overwhelming if we didn't limit it in some way. So we're going to start with intermolecular forces, and then we'll get into liquids. This will lead us right into the phase transitions and phase diagrams, and we're going to end part 1 of Unit 2 with the liquids. In part 2, we'll focus on the solids and spend a little bit more time on them there. Now, we have already talked about intramolecular forces, specifically covalent ionic bonding. That was the whole focus of Unit 1 and the last part of Chemistry 111, to be honest. Here we are going to focus on how the molecules interact with each other rather than how parts of a molecule are bonded together to another. So here we're going to look at the interactions between two or more separate molecules. It's important to note that it takes a lot of energy to break intramolecular forces. It does not take as much to break apart intermolecular forces. These are much weaker than bonding, and they are going to be significant only in liquids and solids. And that's because in a gas, the particles are just too far away to really matter. When you have a liquid or a solid, these particles are incredibly close together, and the closer you are, the more interactions you get. So this would be like your liquid, kind of amorphous but close together. A solid would be a very good crystal in the bottom of a glass, like that. There are 3 types. If you're using a different book, the first may be called van der Waals forces. The textbook we're using in class this semester calls them London dispersion forces. Then there's also dipole-dipole forces, and the strongest of those are hydrogen bonding. Now remember, the intramolecular force is just the bond between 2 atoms within a molecule. On the other hand, the intermolecular force is just the interaction between, say, the partial positive here and the partial negative here. It is an interaction like stopping and saying hi in the hallway to somebody. It is not a bond. It is a temporary interaction that has to do with the proximity and properties of the molecule. So remember, gas particles are very far apart. They move very fast. They are in constant, rapid, and random motion. So because they're moving so fast, you're not going to get any interactions between these. It just doesn't happen. They don't slow down enough. Liquids and solids, on the other hand, the closer you are, the more interactions you can have. The first intermolecular force is London dispersion forces. These are going to be present in all molecules. They are weakest in intermolecular of the intermolecular forces. You can kind of think about these, although they technically come from a temporary unequal distribution of electrons, something like fluorine to fluorine. In theory, the electrons should be directly in the middle here. You can get an occasional or a very, very temporary redistribution of those electrons where you have a partial negative, partial positive. Because these are fleeting, we're talking about probably microseconds, at the most maybe a millisecond. The interactions here are going to be very, very weak and very, very temporary. The great thing about this, though, is it is present in every molecule. So no matter what molecule we're talking about, every single one will have London dispersion forces. And the only thing that can make a London dispersion force bigger is increasing the molar mass of that compound. It's like gravity. Earth is 7 times the size of the moon, and so its gravitational force is about 7 times bigger. The bigger you are, the stronger your force. That is really the basis for London dispersion forces. Now, don't worry about the detail in this table. The big point is, as your molar mass goes up, London dispersion forces go up, which means your melting point and your boiling point are also going to go up. The stronger these molecules hold on to one another using London dispersion forces, the higher these two things are going to be, because it takes more energy to break apart from a liquid to a gas or from a solid to a liquid. Now, London dispersion forces are present in every molecule, but they are the only forces present in nonpolar molecules. And remember, back in Unit 1, we said nonpolar is going to be 2 of the same nonmetal bonded together covalently. Again, this is just a pictorial view of the fact that as molar mass goes up, so does your, I think this is melting points. I don't actually have it on here. The bigger your mass, the stronger the London dispersion forces, the more energy it takes to break apart those molecules from one another. The same thing can be said not only for molar mass. Yes, ma'am, hold on. The same thing can be said not only for molar mass, but for surface. Annabelle. Okie dokie. London dispersion forces increase not only with molar mass, but also with surface area. And that has to do with the fact that the longer your molecule, the greater the distribution of that temporary dipole. So it takes just a little bit longer to go back to the nonpolar equal distribution of electrons. And so you get a slightly stronger interaction just because it takes longer to return to its native state. Now, as far as dipole-dipole interactions go, these are the strong intermolecular forces. Here you have permanent electrostatic distributions that are unequal. So you have a partial positive here, partial negative here. Because these are permanent, they are not fleeting interactions, rather they are permanent interactions. And so you can actually end up getting these permanently formed in polar substances. And because they're permanent, they're strong, it takes a lot more energy to break apart molecules like this. Now, of the dipole-dipole, the strongest type of dipole-dipole interaction is called hydrogen bonding. Hydrogen bonding is going to exist only if you have an NH, SH, OH, and FH bond. Some textbooks will leave out the SH, but technically, guys, these are present in your cysteine amino acids and proteins. And so I'm including it here because if you go into any form of biochemistry, this counts. So now, the other thing that makes hydrogen bonding so strong is that not only do you have this permanent dipole, and it's a big dipole because of the electronegativity differences here, but you can have several interactions per molecule. And so the lone pair here and the lone pair here on this hydrogen can interact with different molecules. The hydrogen partial positive of this goes to the partial negative of the oxygen. Partial negative here interacts with another partial positive. And a lot of times, it's not oriented the way I would like, but this hydrogen will actually interact with both the partial negative here, and it could even be interacting with the partial negative oxygen down here. And so you end up getting many, many interactions per molecule. The thing about that is the more interactions you have, the harder it is to break apart those molecules, okay? So technically, by molar mass and based off London dispersion forces, we would think that the boiling point of, say, water, HF, and NH3 would be way down here in the negative Celsius range. And instead, it's something like 200 degrees off in general, about 150 or so. These forces are so strong that they account for that massive difference from the predicted to the actual boiling point of molecules. Okay, so let's just talk about some molecules, for example. If we have ethane, and then let's do methanol. Let's do an ether. Carboxylic acid. And do methanoic acid. And I'll rewrite this just to show how it's bonded. Actually, we'll go ahead and do it this way. I'll write that out. That's what was wrong. Okay, so go ahead and pause and consider what intermolecular forces are present in each of these molecules. Please try to do this on your own first. Okay, so we absolutely know for this guy, which is just ethane, London dispersion forces. Every molecule has London dispersion forces. It doesn't look like it would be polar because this is going to be equal to that. It should cancel each other out. So we should be good there. What about this guy? Here we have a molecule. Now, usually students want to say, oh, well, this is just a linear molecule, so it's going to the dipoles are going to cancel. But this isn't really linear. Instead, because this oxygen has 4 areas of electron density, 2 lone pairs, 2 bonds. It's actually oriented like that. And so your dipole is this way. So you do have dipole-dipole interactions. We know we have London dispersion because everyone has London dispersion. Because there is no NH, FH, or okay. So here, because we have a permanent dipole, we also have a permanent dipole-dipole interaction. And so this guy should have a higher melting point, higher boiling point than the alkane. And so because of that, ethers in general have a higher boiling and melting point. Now if we come over here, this guy also has a permanent dipole, so we need to consider that. We know it has London dispersion forces. We also know it has an OH bond. That OH bond means it's got to have hydrogen bonding. And since hydrogen bonding is a form of dipole-dipole, Emmeline Grace, Mommy is busy. Please go eat that at the table. Because this is a form of dipole-dipole interaction, we also know we have all 3. So this classification, these alcohols, should have higher boiling and melting points than ethers. And they usually do. Or they do. I don't know of an exception. I guess if they got too big, they might overcome that, but I'm not sure. The highest would be carboxylic acid, because this guy has London dispersion forces, dipole-dipole, because there's this hydrogen, and there's also this hydrogen bonding here. In addition, the dipole of this guy is much bigger than the dipole of this one. And so it's going to have a stronger dipole-dipole interaction, more places to have hydrogen bonding interactions. So overall, carboxylic acids are the most stable at solid or liquid phase. Oops. So if we go back to this, carboxylic acids, or anything that has hydrogen bonding, dipole-dipole, and London dispersion, should have the absolute highest melting or boiling point. Anything with only London dispersion forces would be the lowest. If you have 2 or more things with all 3, you need to consider which one has more places for that hydrogen bonding to exist. Now, in terms of how these intermolecular forces affect liquid phases, we've already talked about melting and boiling points. Now we can actually talk a little bit about cohesive versus adhesive forces. These forces are either, cohesive, meaning the forces between liquid molecules, or adhesive, meaning the molecule of the liquid is adhering to a different surface. And so like you can consider, for example, that's hard to see, the water droplets on a spider web. The droplets hold together in a spherical shape because of the cohesive forces that are present in that liquid. On the other hand, they stick to the web rather than fall the way gravity would intend because of the adhesive forces that exist between the water droplets and the spider web. So again, this is just kind of a bigger picture. So you can kind of see the forces between the liquid itself and then between the liquid sticking to the spider web. In addition, we can kind of consider how these cohesive and adhesive forces affect other properties of liquid. We're going to do that by looking at viscosity, surface tension, and capillary action. Now, viscosity is just the resistance to flow. For the most part, you can kind of see that in terms of like looking at honey or corn syrup versus, which takes a long time to get out of the container, versus something like oil that might spread out and easily flow to cover the surface of a pan when you're cooking. Now, in general, the more intermolecular forces you have, the more those liquid molecules are going to hold each other together, the more they're going to resist flow. So viscosity increases with intermolecular forces, or with stronger intermolecular forces. You may also want to consider, this is why you always have to change the oil in your car. You want to change the oil in your car to put new oil in, new oil that doesn't have particulates or anything that might slow down the flow between the engine parts. Again, don't pay attention too much to the details here, but keep in mind alcohols, alkanes, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. Don't need that part. Like that. Water is H2O. Metals we haven't really talked about yet, but lots and lots of ionic interactions. So we'll just do that. So generally, we think about water as having strong intermolecular forces, and it really, really does. It's just that it's tiny in terms of molecular mass. Meanwhile, something like ethanol has a slightly bigger molar mass, and so it has, in addition to hydrogen bonding, it also has this nonpolar region, which can have a hydrophobic interaction that will also resist flow. So viscosity for water is kind of high if you consider oils, like here. But things with more interactions, like metals with ionic interactions, ethanol, or even honey, which has a ton of intermolecular forces, specifically about dipole and tons of hydrogen bonding. The more intermolecular forces you have, the higher your viscosity gets. Surface tension is just the energy it takes to break apart the surface of a liquid. And you can kind of think about this in terms of that experiment. You can always YouTube this. If you have a penny and you put water droplets on there, I always ask in class, how many drops of water can you fit on a penny? And if you haven't done the experiment, you're like 3, 5, maybe 7. And it turns out that you can actually fit more like 25 to 35, depending on how good your pipette is. The water will actually look kind of like this when you're done, where you have the sides of the penny do not go to the edge of the water. The water would much rather minimize its surface by forming a sphere than by spreading out. And that's because the cohesive forces of the water are so strong, it's really holding itself together. At some point, you end up having gravitational force that will overcome this, and it spills onto the counter. But at first, it's very much, it's really interesting to watch. And you can also see this in terms of, bugs or other things can float on water. You can put a needle, if you lay it lengthwise on the water, you drop it in like this, it will actually float, versus if you drop it like this where there's not enough surface ratio to counter that mass here. Also, you can kind of look at it in terms of a leaf, although leaves, twigs, other things also have to do a little bit more with density. I like the example of the needle because here Steel is obviously more dense than water, but the surface tension of water is able to counter that density difference and hold the needle above the surface. So same thing, the stronger your intermolecular forces, the higher your surface tension gets, with alkanes and so on having the weakest. Capillary action is probably the easiest to visualize. As you have cohesive forces increasing, the likelihood of those molecules wanting to stick together also increases. And so you can kind of look at how if you spill something and it gets anywhere near, say, your lab notebook, one tiny corner of your notebook gets wet, that water acts like a sponge, and the capillary action happens until your whole book gets wet. You can also see it with like a paper towel. You touch the tip of a paper towel to a spill, and you can actually see the liquid following it up using adhesive forces to the paper towel, causing it to rise. Cohesive forces meaning all the liquid follows itself. You can also do this with like straws or capillary tubes, where if you have a vacuum and you just touch it to the liquid level, it will immediately soak up and collect the liquid. You can usually tell this, the easiest place to see this is if they have to draw blood at the doctor's office and they prick your finger. So your finger, there's your fingernail, and you have this tiny drop of blood here. They will just touch this here. The blood fills this area, and then they can run analysis on it either for sugar or iron content, stuff like that. The weaker your intermolecular forces, the less likely you are to go up. So here you can see, because water has really strong cohesive forces, but here is even stronger adhesive forces, the water is drawn up this glass due to those adhesive forces. Here, the intermolecular forces are stronger than the adhesive forces, so you have a convex rather than a concave meniscus, and it will not go as high because it would rather adhere to itself cohesively than adhere to the surface of that glass. So in which image do cohesive forces exceed the strength of adhesive forces? Pause and think about it, please. Here you can see adhesive forces win because it's trying to adhere to the glass more than to itself. Here, cohesive forces are stronger because it's trying to stick to itself and avoid the glass. In terms of how these intermolecular forces kind of work together, you can think about it in terms of phase transitions. So you guys have heard of liquid melting to a gas or gas condensing to a liquid. You may or may not have heard of gas depositing or crystallizing to a solid, or solid subliming to a gas. And here you have an example of that. Usually this is going to be at specific pressure ranges, and we'll talk about phase diagrams in just a minute so you can see that. Solid versus a liquid. You can have freezing and melting happening at the same point of temperature. So here, the more pressure you have, the more likely you are to have, so as pressure increases, the temperature of boiling will increase, and so, or even melting. So here this is melting temperature. So at 1 atm or 1 point something kilopascals, you end up getting water melting at 0 degrees. The more pressure you add, the higher that melting point goes. In addition, it's interesting to note, guys, the energy it takes to go from solid to a gas this direction is the same as from solid to a liquid and then from liquid to a gas. This and this should be equal to each other. And so it doesn't matter if you go from a solid to a gas in one step or in two separate steps. It happens using the same energetic requirements. Think of that like Hess's law almost. Also, just a quick terminology thing. Boiling and vaporizing are the same. Melting and fusing are the same. In terms of phase diagrams, if you are below the freezing or the melting point, those terms are interchangeable, freezing and melting point, because you freeze and melt at 0 degrees Celsius for water. If you are below the melting point, you are solid state. It doesn't matter how cold you go, you are a solid. When you get to this melting point, if you continue, wrong button, to add in energy this way, adding in energy does not raise the temperature at that point. Instead, you are converting between solid and liquid. And so the temperature stays constant until every little bit of that water has been converted to a liquid state. Once all of your molecules are liquid, adding energy quickly raises the temperature of that liquid until it gets to the boiling or vaporizing point. It is only once all of your molecules are in that liquid at that boiling point, adding energy will no longer raise the temperature. Instead, it changes from liquid to a gas, and so you have both phases present at that point until it is all gas. Once all of your molecules are in the vapor state, increasing temperature, once all of the molecules are in the vapor state, increasing the energy at this point will actually increase the temperature again. And so you can kind of see the temperature of steam rises almost instantly. Has to do with the specific heat of water versus steam. This is already broken apart, so increasing the motion of those molecules is going to be much easier. It's also why you can actually get just as bad steams, if not worse, from steam as you can from water. Hot water, highest temperature is 100 degrees. The problem with water is if you don't get it off you, if you get hot water on your clothing, you should remove the clothing immediately so that it doesn't hold it onto the skin and continue to do damage. Meanwhile, if you have hot steam, you can generally move back from the steam pretty quick, but the temperature is a lot higher, and so you can have just as bad of an influence there. Last part of this unit, part 1, liquid phase, is phase diagrams that look like this. Here, most things, if you increase your pressure, the melting to freezing line goes in a right slant, and it's because technically the solid takes up less space than the liquid in most molecules. Whereas like a liquid is kind of like, oh, there's just a little bit here. Not compressible per se, but just a little bit more space. So the higher your pressure, the more likely you are to be a solid. You also have your triple point, where you have gas, liquid, solid, all present at the same time. Sublimation, deposition line, melting, freezing line, vaporization, condensation line. We don't really talk about supercritical fluids in this class. But after the critical point, this phase line between a liquid and a solid, between a liquid and a gas, is kind of blurry, and you end up getting a supercritical fluid that has properties of both, as well as some charges within those molecules. Interesting to read about, possibly involved in a couple of your later classes, depending on where you're going. This is for most things. This is for water. Water has the liquid phase taking up less space because in ice you end up getting those hydrogen bonds between molecules, creating holes in the molecule itself. And so you end up getting these spaces between the molecule or within the molecules. And so the solid state takes up more space, so increasing pressure makes it more likely to go to the liquid phase where less space is used. Very different from basically every other substance there is. So that's the difference between these two phase diagrams. Your reading does a really good job of talking about how to identify parts within a phase diagram. So make sure you're looking over that for this. And with that in mind, that is the end of part 1 of Unit 2.